Welcome everybody to this series of seminars. Now that the name also changed, so it's in probability and statistical mechanics. And it has been organized since more or less, well, maybe a year ago. And it's a joint seminar with the Portugal, Brazil, Argentina, and several universities in these countries. And it's always, so for people who don't know, it's always every Wednesday. And so all Wednesdays at 16 UTC time. This is very important, UTC time zone. And today we have as a special guest, Makiko Sasada from the University of Tokyo, that I would like to thank so much for accepting this invitation, especially because for Makiko it's too late. It's 1 a.m. in the morning. So thank you, Makiko, for being with us today. And well, so you can see Makiko is going to talk about on the Varadhan's decomposition theorem in a general setting. Makiko, the floor is yours. Thank you so much.
Thank you. Yeah, thank you very much for this nice invitation. I'm very honored to speak here in front of great audience. Okay, so let me start. So this talk is based on joint work with Kenichi Banai and Yukio Kametani. So they are algebraic people and so geometry people. So it's really a great joint work over different fields in mathematics. And yeah, I will start very beginning. So the background of this talk is about non-equilibrium statistical mechanics. And so we want to derive macroscopic evolution equations from microscopic dynamics, and especially so even diffusion equation from simple microscopic models is still, yeah, has been studied very intensively, as we can see from today's workshop. And of how to derive macroscopic equation rigorously is the most important question as a mathematician, I think. And so one of the answers is hydronic limit. So yeah, I will not explain what is hydronic limit, and I believe almost all of you know what they are. But so motivation for our work in hydronic limit is as follows. So far, all previous works in this area some way case-by-case analysis of specific models, I believe. And of course, there does exist a model-independent strategy like entropy method or relative entropy method, and also many ideas. But I think there's still no general theory, and especially I'm in mind non-gradient cases. And in particular, so there are many interesting models for which the hydronic limit is expected to hold, but this has not yet been proved. So our very ambitious goal is to initiate something universal general theory of hydronic limit in a general setting. But more specific motivation is about decomposition theorem of Varadhan's decomposition theorem. So yeah, actually this key ingredient for deriving the hydronic limit for diffusive case is this decomposition of closed forms on an infinite product space. So that is our main target to make some generalization. And so roughly the setup is, so we consider these infinite product spaces, so infinite dimensional space, and we consider something called closed forms or exact forms, which is analogous to the one form and so differential forms, but on this infinite dimensional space. And again, in analogy with cohomology theory from geometry or topology, we need to prove that the space of closed forms over the exact forms is actually a finite dimensional space, and typically it is the dimensional space, and this space is actually characterized by some explicit expression or in terms of a conserved quantity or quantities. But yeah, actually this becomes RD when there's only one conserved quantity, and if there are two conserved quantities, then this dimension of this space should be 2D, and so on. And if we have three conserved quantities, maybe this becomes 3D. But yeah, so far we know this just case by case, but we actually didn't know much about the general or universal structure of this form, I think. So why this dimension, for example, is not clear from the existing proof of Varadhan's method, because this dimension appears like something like just by incident or by accident. So I really wanted to understand why we have this dimension, and also why we have this explicit expression in terms of concept of quantity in a very universal way. So that is my motivation. And so we aim to construct something rigorous and model-independent criteria for such decomposition to exist and understand the underlying universal structure. And of course, if we can find some intuitive or simpler proof for this non-gradient method, it should be very nice. And of course, we want to solve open problems by this new approach. That means some more classes of models. And our main idea is actually the formulation of this decomposition theorem in a very general setting. So just by give this general framework, we can learn many things. And crucially, we separate geometric data and symmetry data. Maybe this green is not so good, but symmetry data and stochastic data of the models. So if we want to define some microscopic models, we always need these informations usually, especially for the non-gradient method works, or when the non-gradient method works. So we always have this information, and so our approach is actually we separate them and we make clear what is the role of this data. So I want to explain this today. But so I want to start one very typical example, which is well known, but the exclusion process on the D case. In this case, the state space is just the product of this the 2-point sets. And the eta is a configuration of particles, and just eta x equal 1 means there is a particle at x, and so and 0 means there's no particle. So yeah, maybe I think all of you know what is this. And so we the model data is actually jump rate rxy. So that is the frequency of the jump from x to y, and so the generator of this exclusion process is given by this way. So if eta x is 1 and eta y equals 0, then so particle jump from x to y. And so eta xy is the configuration obtained from eta when a particle x at x goes to y. So yeah, we only need to define this for this case, but maybe we can define also the just exchange occupation variable at x and y, and our xy is here as an input in generator and as a jump rate. And we always assume that the translation invariance. So here already we use symmetry of the state space in some sense. So we have this translation operation, and also we always assume that local interaction. So our xy are local functions actually, and also finite range. This means the jump occurs only for short range. So they are a bit different, but both control the locality of interaction, and the locality of interaction is very important. And also we always assume non-degenerate condition. That means if the number of particles are fixed, then any configuration can move from one to the other in some sense. So at least in finite case, finite site case. So more precisely, we can say this way. But so these are somehow most important properties of microscopic models. So when we generalize the model, we always think about this condition, and we want to make more general condition which relates to this, or which means this for exclusion case. And additionally, we also sometimes assume these conditions. So first, a nearest neighbor means actually the jump occurs only between the nearest neighboring sites. And so simple means jump rate does not depend on eta. And also we often assume that the Bernoulli product measures are actually stationary for this process. And especially if a symmetric case, that is this case, then Bernoulli product measure becomes a reversible measure. But also we can consider a mean zero case. That is, okay, it is not reversible, but the Bernoulli product measure is still stationary, and also the average current is zero for any direction. So this case is also in the diffusive setting. And other case is so reversible, but which is not with respect to product measure, but some Gibbs measure. So this case was also studied before, even for non-gradient case. And so, yeah, these are typical case assumptions we may assume in some cases. And so the most simple example is a simple symmetric nearest neighbor isotropic exclusion, which is given by this one. So maybe, yeah, it is well known, I think, for all. And hydrodynamic limit on the diffusive space-time scaling is known for many cases. And so, okay, we consider reversible or mean zero case, and because we are interested in a diffusive case. And so universally, we expect this type of hydrodynamic limit equation for this case. And here we have diffusion matrix, diffusion coefficient matrix, and rho is the density of particles. So the density of particles is only a macroscopic parameter, and we expect this will follow this PDE. And what is rigorously known is following. So for symmetric and simple case, which is not necessarily nearest neighbor case, yeah, actually we get a linear equation in the limit, and this is explicit. But also for reversible and nearest neighbor case, actually this is important, yeah, somehow. So for non-gradient method so far. And so for product reversible measure case, which is given by Funaki Uchiyama, and the non-product case is given by Varadhan, that actually this hydrodynamic limit equation holds, and the diffusion coefficient matrix satisfies this variational formula. And what I want to emphasize here is that this form is universal. So it's it does not depend on the measures. And of course, new rho depends on is different for the first case and the second case. So new rho is a reversible measure. And our tilde is actually R itself for Bernoulli case, product case, and non-product case, so our tilde should relate to R as this is a Dirichlet form coming from the jump rate. But important point is, anyway, we have this part. So this part is important. And okay, so here we have some infinite sum of translation. And here we have something which is not translation invariant, but so each x is the number of particles at x, and xj. So yeah, so this part is universal somehow. So, and actually, even if we change the model, still we see this form, yeah, this universal form. And here we see the conserved quantity. But yeah, so we expect this should be something very universal, but so far we don't know how, yeah, we prove this in a general setting, I think. So that is a point. And even mean zero case, yeah, we have more complicated variational formula, but the essential part is actually reduced to the reversible case. So I want to focus on reversible case from now on. And then the point of our idea is actually we study the graph structure of the configuration space. So now we assume our x, y, eta is positive is yeah, if and only if this is positive. So that means if we can x can particle can jump from x to y, then also y goes from y to x. So yeah, so this if the process is reversible with respect to some measure, then this should hold. And then so our x, y, eta is positive means so from eta to eta xy is a possible transition, just one step transition. So yeah, this gives us the graph structure of the following. So the vertex set is just the configuration space or configurations, all of configurations, and the edge set is just a pair of eta and eta xy, where this rxy is positive. So this means just the set of all possible one-step transitions. So it's very simple set. But so this is actually geometric information of the model. So from this vertex set and edge set, we can see which configurations are connected just by one step, but we do not know what is the speed. So, and this is the most important idea, which is very simple, but, and then we can consider this graph and graph cohomology, which is very simple. So just zero form is a function on the vertex set. So, and one forms are just forms the functions on the edge set. And from one form, we can actually obtain the set of functions again on the configuration space by this relation. So for xy means actually all edges, or okay, so maybe we can just keep this omega xy, and omega xy is each omega xy is just function given by this way, and then the derivative is also defined in the usual graph standard cohomology way, just by so edge. So the f of some edge is just given by the difference of endpoint and origin. So eta xy is the terminus, and eta is origin of this edge. So this is a very general graph cohomology. And then assume that jump rate is reversible and nearest neighbor. So then yeah, actually we consider okay, so that is not so important here, but so we are interested in local functions because this C0 is too big for us somehow. So it's not the space we're really interested in. So we consider local functions, and then we can introduce the notion of local forms. That means all of omega x, y, these functions are local. But here, yeah, so here I restrict the pair of xy, just x and x plus ei, because now I'm interested in the case of nearest neighbor case. So then we only consider x and x plus ei case, and the reversible means just actually x plus ei and x, it's somehow same for x plus ei. So we only consider these functions, and if they are all local functions, then we call omega its local form. So then we consider local function and local forms. And of course, this d is now given by this way. And if we have local function here, then we get a local form here. And also we want to introduce shift invariant forms. So that is omega x plus EI. This is a function on the configuration space is given by a shift of omega 0 EI for all x. So this class is a shift important class, and to define this class, we really need the information of shift or translation. So far we use the geometric information of the model, and here now we use translation symmetry information, and finally we introduce inner product in this space. So it's a analogy to Riemannian metric. We can consider we have some manifold, and then we have some one forms, and then we introduce the inner product of them. So this is really now we need the information of stochastic information or temporal or speed or measure. So here we use this Dirichlet form related to the jet generator, and then we take its completion, so of local forms with respect to this inner product. Then we can consider L2 forms, class of L2 forms. So so maybe it's a bit quick, but so to state Varadhan's decomposition theorem, we need the following data. So first, configuration space. What is this space? And shift operators, tau x, all of shift. And so differential operator. Actually, differential operator define the connection or the edge set somehow, edge set of this graph. And inner product determined by new row, the reversible measure, and jump rate. So the red ones are geometric data, which I will generalize later. And this green one is symmetry data. And this is stochastic data. So, and now the Varadhan decomposition theorem for the exclusion process is stated in the following way. Okay, so this is a product case, but also Varadhan and Yao proves the other mixing Gibbs case. And now suppose this omega in the shift invariant closed forms. Okay, so I didn't explain what is closed, but I will explain later this. And if we have some closed shift invariant L2 forms, then this should be decomposed in this way. So first term is coming from something shift invariant. So it's a formal sum, but this derivative is well defined, and so Fn is local functions, and this part comes from conserved quantity Cx, which is a function given by this one, and this term is not shift invariant. So that is a point, and and we have this d-dimensional space which is not shift invariant. So we call this part exact forms, and this part is not exact forms, which are d-dimensional space. So in this L2 space. So that is Varadhan's decomposition theorem, and this is actually very difficult to prove. But the point is this form is very universal, and it seems like it's nothing to do with this measure or rate of this form itself. And these functions are defined only if we know the information of geometric data, for example. So our motivation was we can consider this decomposition theorem in the forms for local forms, not L2 forms, but the forms before this completion. So this class is nothing to is independent from the choice of Dirichlet form or these measures or jump rate. So for this smaller class of forms, if we can decompose in the similar way, then maybe it will give us some more information or more intuition of this result. And of course, this form explicitly appears in the variational formula if you remember this form. So this is the key of the diffusion matrix. And other typical microscopic models, for example, generalized exclusion process on this space. And so now we can put 2 or more particles on each side. And so the dynamics is if there's the particle, then this moves to nearest neighbor site, for example, or multicolor species, color or species exclusion process on this space. Now, so 0 or 1 or 2 is not the number of particles, but instead the color of particles. And here I want to emphasize that in my talk, I always allow the exchange of positions for any different colors. So not just by a color particle and 0, but also this type of exchange is allowed in my talk, because if we want to consider a degenerate case in the same setting, it's also a bit complicated. And so we always consider non-degenerate case. And non-degenerate means if we fix the number, all the conserved quantity, then our configuration is so irreducible. So, well, yeah, the space of state space with fixed conserved quantity is irreducible. So I want to consider this case. But the speed can be different from between different colors. And the decomposition theorem is already, of course, shown for several specific models, like exclusion or generalized exclusion, multicolor exclusion, or lattice gas with energy, which has 2 conserved quantities. But there are very few results with multi-conserved quantities. And also, yeah, this multicolor exclusion here, I mean, this is a degenerate case. So the class of closed forms is also limited for some special class. But yeah, this is, of course, difficult because of degeneracy. And for continuous models, as far as I know, there are, I think, 3 results, only 3 results for this decomposition. So one is Ginsburg-Landau dynamics and also stochastic energy conserving model. Okay, I'm sorry, I know, but yes. Okay, so there are at least 3, yes, and the system of oscillators and so on. But the point is, for all models, the lattice is CD and the interaction is nearest neighbor. So, and this is actually, if we want to generalize some part of the discussion for finite range, there's some obstacle. Yeah, and the stationary measures are all product except for the exclusion process. So still there are many ways of generalization or extension. And so, for example, our multi-species exclusion process case is open. Yes. For general case without degeneracy, but multi-species case. And energy Ginsburg-Landau model, for example, dynamics, which is on R plus CD, is also open. Even spectral gap is known. So there's some other difficulty. And energy exchange model, another, it's a jump type model on this state space, is also open because
so, sorry, Makiko, if I may.
Yes.
You're saying multi-species exclusion process is open, but Castell proved the spectral gap at least for 2 species, no?
Yeah. So I mean, so multi-species means so color. So you mean multicolor case or?
Yeah, multicolor case. Well.
Yeah, color means the jump rate is all same.
Yeah.
No? Yeah, so I mean here
okay.
means,
yes. Sorry. Yes, you're right. Thank you.
Speed are different. Yeah. Okay, so thank you for your comment. And yes, so this case now the jump type operation give us some kind of integral operator as nabla usually. So, and this is really challenging because it's hard to define the notion of closed form even. So yeah, there are many interesting open problems, and also finite range interaction case or models on general crystal lattice such as hexagonal lattice or diamond lattice and so on. Also was an open, and the stationary images which are not product is really challenging, I think. And at least our result applies for Varadhan's decomposition theorem level. This multi-species exclusion process is now solved, and also finite range interaction is okay, and models on general crystal lattice such as hexagonal lattice and so on, it's also yeah, okay. So, but of course, I want to make more precise what general result we have. Okay, so now I will explain rigorously what we did. So first, our general framework is as follows. So geometric data means has 3 parts. So S is now local state space. So this is very general. So any set, just a 2-point set or this finite set or R or something. And this is a state space for single vertex. So just 1 point. And the phi is now a function on S times S to S times S, and which we call interaction. So in this level already we somehow restrict our framework for discrete setting in some sense, but for our result, some of our results apply also for non-discrete case, but it's not so interesting. But yeah, so for example, phi is just S prime is exchanged. So this is exclusion case, and this is for generalized exclusion case. And this give us the dynamics on between 2 adjacent vertices. But I will explain it a bit more later. And so finally, XE, which we call local, is just a connected locally finite symmetric graph. And for example, ZB and this edge set, which is a nearest neighbor set, all edge sets, is for one of the example. And the other is this is our nearest edges. And here I put edge where we the jump occurs, or so the interaction occurs. So this edge set really includes information of the range of interaction. So if so finite range case, we can change this edge to this one, for example. And of course, we can also consider hexagonal lattice or any other crystal lattice, so on. And the symmetry data is actually the group action, which and group, which acts freely on this locale. So this underlying space, underlying graph. So that is the point. And finally, stochastic data, we mean probability measure on this space, and also jump rate, the set of functions. This is just local functions. And E is this E. So for each edge, we consider how often this transition occurs. So the local state space, so this S is just, again, non-empty set. And maybe we put some base state here, we define, we choose, but it's not so important. So for X01 or this multicolor or generalized exclusion. And interaction is a bit complicated. So we have this condition, but it's not so scary. So here, iota means this is just a map exchanging components. So if phi is also this one, so just a chain exchange component, then of course, if we apply this operation false times, then this goes back to original one. But if this is the generalized exclusion type interaction, then it becomes a bit more complicated. But still, we can check these holes, and this essentially means if we have this, okay, so if this particle moves here, then okay, well, from one by one interaction, and if this is this direction, so if we consider this HE, then we have this interaction. Then if we change the direction, so here if we see this in different direction, opposite direction, and apply the same transition, then this and we go to original direction, then we go back to the original one. So that is a condition. But if the first step, if at the beginning, if we cannot move from the first configuration, then we do not need this condition. And this condition ensures that the associated configuration space, which is a graph, is symmetric. So this bigger graph is symmetric. So that is important for us. So, and this is almost the condition for the reversibility. So for stochastic case. And for example, phi is this one, as I already explained, or multi-color case, phi is just exchange color, or even species case. So the point is geometric data does not depend on jump rate. And the locale is already, I explained that it's just connected locally finite and simple symmetric direct graph. So that's all somehow. But the important thing is this H set determines the graph distance between vertices of X, which we will use to measure how local the functions are. So we introduce uniformly local functions and uniformly local forms. So, and the locality is measured by the graph distance of this underlying graph, so ZD or hexagonal lattice or so on. So that is the important role. And the interaction occurs only on a pair of adjacent vertices, as I explained. Okay, so these are examples of locales. And so now we introduce a notion of conserved quantities, which is just defined by S and phi. So we do not need information of locale, but if we know S and phi, then we can define what is the conserved quantity. And also from these three data, we define a graph structure called a configuration space with transition structure. And the second one is easier, so I will explain this first. So configuration space is just a product space of S to X. So it's very simple, I hope. And now transition or edges defined in this way. So now from any eta configuration and the edge E, which comes from the underlying graph, then we define eta E by this way. So eta E X, it does not change if X is not origin or terminus of E. So it's the same way as exclusion case. And if for at OE and TE, we apply this interaction phi. So, and by this way, we can define eta E, which is given by just one step transition. So if we have eta and if we have E, then we get what is eta E. And sometimes, of course, they are same. But anyway, so we get edge set of big configuration space. And this is symmetric by assumption of interaction. And so this we call configuration space with transition structure. And this is a graph, but it's not so nice graph because it's not countable or not locally finite. And so typically this has infinitely many connected components, because if we fix the number of particles, for example, then of course they are not connected. So it's not so it looks not so good object, but still macroscopic information of the model may be recovered from this graph using cohomology. And that is the idea. So, and maybe cohomology is not so well known, I think, in this community, but yeah, I want to say a bit about this. So yeah, if X, the underlying graph, is infinite, then this graph has an infinite connected component. So this means the dimension of A is 0. So this is a dimension of kernel of D is infinity, and so we cannot see anything interesting. But if we change the space of functions to uniformly local functions, so that is a point, but unfortunately, I don't have the time to explain what is this, but for example, these functions is in this class, and also, sorry, tau maybe for ZD case, for ZD, for X in ZD and XJ, X, for example, this is also in this class. So our another main idea is actually in our theory, they are not formal sum, but really well-defined object. And so, and we define this, then we can consider the space of functions, which includes these functions. And also we introduce uniformly local one forms, and this is easy. So it's easy to define, and this is a subset of local forms. And so locality is uniform. So just such kind of definition. And then D, this operator is again the same as before, because this is natural one, which relate to our generator. And one form is closed if the path integral is 0 for any closed path. So that is, it looks like tautology, but it's, yeah, this is actually what we really want to study. And then Z1 uniform is just the closed forms in this uniformly local forms. And so conserved quantity is defined in this way. So it's very simple. So just a function on this 1 point set is conserved quantity if this base point, at base point, it takes 0, and the sum of C is conserved under this interaction. And this condition is important because we do not want to count the constant, and constant function always satisfy this condition. And this is not important class. And this is also appears naturally if we consider conserved quantities to take average 0, for example, if we have measure. But even we don't have any measure, still we can define in this way. And then this class of conserved quantity is really a vector space, and we can consider the dimension of this vector space, and this is very important invariant. And this number is actually can be calculated by the cohomology, and this can be understood as a number of macroscopic parameters in our hadronic limit. Okay, so maybe I should go a bit more quickly, so because I didn't say anything about the main result. So first main result is the local form version. So now consider H0 is the zeroth cohomology, and H1 is the closed form over exact form. Actually, exact form means the image of D. So this is actually the class of closed over exact, but we do not introduce any symmetry data, so any translation. So now if we assume S5 is phase-free quantified, so this is equivalent to the non-degenerate condition. So if we fix conserved quantity, then any configuration is can be reached by some transitions. And then if the locale is infinite, that is very important condition. And I'm sorry, but I cannot explain some conditions here, but it's just about the graph condition. Then this H0 is has a is isomorphic to this space. And so this means if the conserved quantity is the class, this dimension is finite, then this is also finite, and H1 is 0. So this is actually the main of our result, and which we call cohomology theorem. And this result is based on the geometric data only. So of course, there's no spectral gap or no any measure information. And at least Euclidean lattice case, ZD, ED satisfies the condition, this condition, some condition in the theorem for D bigger than or equal to 2. But D equal 1 case, actually, we have a counterexample if we have multiple conserved quantity. So that is also something we see interesting. And now if we add the symmetry data, so if we assume G, the group acts freely on this locale underlying graph, then under the same condition, the same first theorem, if the rank of G of abelian averagization of the group G, or if we consider G just ZD, then it's ZD itself, then this cohomology, so this is shift invariant clause forms over shift invariant exact forms, shift invariant exact forms is given by this one. So now it's isomorphic to the dimension of conserved quantities times D. So if this is one-dimensional space, then this becomes D. And this is a simple corollary of cohomology theorem, actually. So the most difficult part was here. So this one, cohomology theory, and this D appears only because this symmetry of the group. And also from this, we can obtain explicit decomposition in this way. So, okay, but so once we fix the fundamental domain and also the basis of the group action and also basis of conserved quantities. So usually we always fix some basis of conserved quantities and so the D or so the group. So we have this form, but yeah, of course, this Aij, for example, depends on the choice of these bases. But once we fix them, then we have this unique expression. Yeah, okay, so maybe I will skip here. And so now, recently, we also obtained L2 version, so original Varadhan's version in this general setting. And so this partly appears already here. So partly means we only prove, only give in this paper the case where the underlying graph is ZD and the nearest neighbor, because the extension will also make the paper too long. So, but so now we add the stochastic data. Now mu is probability measure on this space and R is a jump rate. And we need more conditions for this case, of course. And so first S is finite. This is strong, but essentially this case is only the case where it can work so far. And G is ZD and X over G is finite. So maybe we can generalize this a bit more, but so far we are not so sure. And R and mu are G invariant. That is natural condition. And and this is also strong condition that mu is product so far. But under assuming this and also if we have uniform spectral gap estimate, of course still we need this. But then universally, so generally we have this decomposition that is Varadhan's decomposition theorem. So that is our main result. And once we have this, and as before, if we fix this fundamental domain and also basis of this group action and the basis of this concept quantities, then we have the same decomposition as Varadhan's result. Okay, so and some remarks. So we actually use our local form version result to prove this L2 version result, because otherwise we need to find this specific form of case by case, but we can avoid this case by case discussion because we have the formal local version result, which characterize already this part. And this is applicable to multi-species exclusion process and finite range case, and also crystal lattice case. So we can somehow generalize existing result. Okay, so maybe I will stop here. Thank you very much.
Thank you so much, Makiko.
Thank you.
I think I'm... Hi. So now, questions from the audience. I hope you hear me.
Well, I have some questions. Thank you very much, Makiko, for this very nice talk. So do you get also in these models a variational formula for the diffusion coefficient? Can you comment on that?
Yes.
Then a second point, a second question would be these forms, which are closed forms, which are not exact forms, were in some sense related to the current. So, and the number coincided with the current. So do you get exactly the same structure in your models? And then the third question, you comment on the difficulty of non-nearest neighbor. I would have thought that it wasn't a big obstacle, but maybe I'm wrong. So could you comment on that?
Yeah. So just my daughter will come. But, okay, so
she didn't like the question.
Thank you. Yeah. So first, let me see. Yes. So variational formula is we can obtain, and actually, I think already we obtain a dissipation inversion or sorry. So. Equilibrium fluctuation. So we can prove also in this general framework equilibrium fluctuation. So and I believe we already have proved it. So there's no obstacle. And sorry, what was the second? It's finite range case? No.
Yeah, finite range, but maybe we can interrupt. I mean, we can ask. I can ask later.
Sorry, but
yeah, sure.
Yeah, but I want to say, so finite range case, the difficulty is, okay, maybe, okay, now it's easy. Yeah, so finite range case, we need to count the number of boundaries. So I think you remember. So if we need the boundaries of HE and the other E tilde or something. So, and there we use a very specific form of this fundamental domain approximation of a lattice box. So, yeah, maybe in our paper in the, okay, so in this archive of this, so this one, yes, no. In this paper, I already mentioned in the introduction that where is a difficulty of finite range case, and in the section 5 or something, I give explicit remark. So this part is not easy to generalize for finite case. So and in other papers, so this paper is only for nearest neighbor, but in next paper, which we are now preparing, we explain how we can solve this difficulty. So here, actually, we need some techniques to avoid this difficulty. Sorry. Yeah, thank you very much for your question.
Thank you.
Yeah, thank you.
Thank you, Makiko. More questions from the audience?
Yeah, I really hope to hear the question. So please not hesitate to ask.
Okay, maybe we should leave the questions for another day.
Yes,
Makiko.
just Makiko, will your slides be available at some place?
Yes,
Okay.
we will ask Makiko. We'll ask everybody to put the slides, and I will send an email saying where we have them. But usually, if you check this website, Clément, you will see them there.
Yeah, thanks.
Okay. Good. Very good. So, Makiko, thank you very much for this. You were really scared that your daughter wakes up, and she woke up really precisely at the moment of questions. But anyway, thank you so much. It's really late for you. And well, let me advertise a bit. So we are in the middle of another workshop. So if anyone else wants to join us for the last talk of Evita, I put the link here, so it's in Zoom now. Let me see if everybody can see. Yes, so in case you want to join us, it's another Zoom link. And if not, we'll see each other next week. Claudio, it's Davide, right? It's Davide Gabriel. Exactly. Yes. Very well. It was very nice to see everybody, even if online. So see you next week, or in a minute in another room. Bye. Thank you, Makiko. Thank you so much.